In this video, we're going to look at reaction stoichiometry, which is how we can use the balanced equations that we've now learned how to make to predict quantitatively how many moles or grams of a substance will be formed or used up in a chemical change. The key to using stoichiometry is to understand the concept of stoichiometric equivalencies. The coefficients that are in a balanced chemical equation reflect the relative quantities that react as a reaction takes place. So for example, 3 moles of sodium hydroxide, NaOH, will react with 1 mole of H3PO4, phosphoric acid. Or for every 3 moles of NaOH that react, you're going to produce 1 mole of Na3PO4, sodium phosphate. Or for every 3 moles of NaOH that react, 3 moles of water will be formed. Or for every 1 mole of sodium phosphate that will form, 3 moles of water will be formed. So you can compare any quantities in a chemical reaction. The BCA chart, or before change after chart, is a useful way to organize predictions about change. This is especially helpful when you're starting out. There are more efficient ways to go about doing these calculations, but this is a very good way to start thinking about these changes. The change line, the middle row here, shows the stoichiometric equivalencies. We have a minus 3 moles under sodium hydroxide in this chart because it's losing sodium hydroxide. It's a reactant, so that's negative. Minus 1 for phosphoric acid because that's losing. But we have a positive 1 because a coefficient of 1 on Na3PO4, and it's a product, so it's going to be gaining moles, and positive 3 for water. So the negatives are for loss of reactants, the positives are for gain of products. So let's say we were going to react 3 moles of sodium hydroxide with 3 moles of H3PO4. We start out with no moles of either product in this reaction. After the change takes place, we're going to lose all the moles of NaOH, 3 minus 3, so there will be none left. We'll lose 1 mole of H3PO4, and so there will be 2 moles left. We will gain a mole of sodium phosphate, so there will be 1 mole of that, and we'll gain 3 moles of water, so there will be 3 moles of that after the change takes place. Let's use a BCA chart to do this example problem. How many moles of Na3PO4 will be formed? So what we're going to want is what's going to appear down here if 0.366 moles of NaOH react. So we'll put 0.366 moles in here. It doesn't tell us any information about H3PO4, so let's assume that we just have kind of an unlimited quantity. Before the reaction, we don't have any product at all. We will lose all 0.366 moles of NaOH if we have an unlimited supply of H3PO4. Because the mole ratio is 3 to 1, we will lose 0.366 moles over 3, only 1/3 the amount of H3PO4. We will gain 0.366 moles over 3 moles of Na3PO4, and we will gain 0.366 moles of water. So in the end, we will have 0.366 moles of water, and if we take 0.366 and divide it by 3, we get 0.122 moles. That's how many moles of Na3PO4 we would get when we're done. We won't have any NaOH left, and this, we still won't know anything about that. Here's another way of doing this problem. We can take a dimensional analysis approach to this problem. So here's how we can set this up. We'll start out with our 0.366 moles of NaOH. And we're going to use a stoichiometric equivalency, or a mole ratio, as a dimensional analysis factor, knowing that we want to end up with moles of Na3PO4. Remember that our equation is 3 NaOH plus H3PO4 makes Na3PO4 plus 3 H2O. So the ratio is 3 sodium hydroxides to 1 Na3PO4, or if we flip it upside down, 1 mole of Na3 3PO4 for every 3 moles of NaOH. By setting it up this way, the moles of NaOH cancel out, and we're going to get moles of Na3PO4, which is what we want. And of course, the answer is the same as if we do it with the BCA chart. It's 0.122 moles. When doing stoichiometry problems, it's important to recognize that this only works for moles. The mole quantities, or stoichiometric equivalencies, they're only valid for moles. So if we had to answer this question, how many moles of H2O would be formed if 0.366 grams of NaOH react, we have to add a step into our problem solving. So I could do that by going 0.366 grams NaOH, and then converting into moles by just using the molar mass of NaOH, which turns out to be 39.997 grams per mole. So with grams canceled out, now I have moles of NaOH, and I can proceed with my mole ratio. So it's 3 moles of NaOH, and if you recall the equation, there was a 1-to-1 equivalency, or a 3-to-3 equivalency, with moles of water. And so when we calculate this all out, we're going to have moles of water, because moles of NaOH have now canceled as well. The math is going to be 0.00915 moles to 3 significant figures. Here's one where the beginning and the ending of the problem are mass. So just recalling our reaction, we're going to start out with 0.366 grams of water. We need to convert this into moles so we can do stoichiometry with it. Ultimately, we want to get grams of H3PO4 over here. The molar mass of water is 18.015 grams per mole. So by putting the grams on the bottom, we cancel it, and now we have moles of water. Now we can do stoichiometry. There are 3 moles of water for every 1 mole of H3PO4 that reacted. So now moles of water have canceled, and then we can convert to grams. The molar mass of H3PO4 is 97.995 grams per mole. So moles are going to drop out, and we have just what we needed, grams of H3PO4 left for units. When you do the math, it's 0.664 grams of H3PO4. Previously, we solved the problem where we had an unlimited amount of H3PO4, and we wanted to find out how many moles of sodium phosphate were going to be produced from 0.366 moles of NaOH reacting. Now we have a situation where we don't have an unlimited quantity of H3PO4. This helps us explore a concept called limiting reactant. It's important for us to figure out sometimes which of the 2 reactants is going to run out first, and that will limit how much product gets produced. So in this question, it says we have 0.366 moles of NaOH, and we also have 0.366 moles of H3PO4, not an unlimited amount like the last time we did this problem. Our goal is still the same. We want to find out how many moles of Na3PO4 are formed. There won't be any product of either kind. Now imagine that we use up all the H3PO4. Because of the 3-to-1 ratio, we would have to use up 3 times 0.366 moles of NaOH. And we don't have that much. So that means NaOH must be the limiting reactant, because we're going to run out of it before we have the chance to consume all the H3PO4. Now that we know that, let's start this problem over again. We're going to lose 0.366 moles of NaOH. We're going to lose 0.122 moles, that's a third of 0.366. And we're going to gain 0.122 moles of sodium phosphate and 0.366 moles of water. So the answer to our question is 0.122 moles are produced by the reaction when sodium hydroxide is limiting it in this way. Even after you've calculated the amount of product that you should theoretically be able to get based on the limiting reactant, sometimes when you run the real reaction, you don't get the amount of product that you expect to get. There are a few reasons for this. One of them could be losses. Sometimes they're avoidable losses like leaks or spills, things like that. Sometimes they're unavoidable losses like your filtration system just can't possibly collect all of the product. Sometimes there are competing reactions. So the reactants that you're reacting together produce the product that you're interested in, but they also produce another product, and that uses up some of the reactants. Or sometimes product reacts with another product or with one of the reactants, and that uses up some of the product. And so there's a bunch of reasons that you might end up with not as much product as you actually predicted you would get. When that happens, we use something called percent yield to try to keep track of that. So the calculated amount that you would get based on stoichiometry with the limiting reactant is called the theoretical yield. If you actually do the reaction, the amount that you get is called the actual yield. And the percent yield, as a percentage, is just the ratio of the actual yield to the theoretical yield. Now, why this is useful is after you've eliminated all the obvious mistakes and got it down to just unavoidable losses, you can often get a very consistent percent yield. And that allows you to make good predictions about how much reactant you would actually have to start out with to get a target amount of product produced. Let's do an example calculation to help get at the idea of percent yield. So we want to know what is the percent yield if 50 grams of nitrogen reacting with 50 grams of hydrogen produces 56.7 grams of NH3. We can't do stoichiometry with grams, so we'll have to convert this into moles. And there are two ways that you can approach this. You could change 50 grams of nitrogen into moles of nitrogen, and 50 grams of hydrogen, convert those into moles of nitrogen, and then set up a BCA chart. We've done that before. The other thing you can do is run two-dimensional analysis calculations based on each of these two being the limiting reactant, and then find out which yields the smallest theoretical yield. Before you can do any of that, you have to have a balanced chemical equation. We've seen this before. Nitrogen plus 3 hydrogen is going to produce 2 NH3. Okay, so that's the equation that's going to give us the mole ratios, the stoichiometric equivalencies that we need to make our calculation, no matter how we do it. I'm going to do the dimensional analysis approach. I'm going to start out with 50 grams of N2, and then I'm going to find out how much NH3 in grams can I make from that. So the first thing I have to do is use the molar mass, which is 28.014 grams per mole, and that gives me moles of N2. From my balanced chemical equation, I know that 1 mole of N2 will produce 2 moles of NH3. So now moles of N2 have canceled out, and I know how many moles of NH3 have been produced. But I want grams, so I'm going to use the molar mass of ammonia, which is 17.031 grams per mole. And that will allow me to calculate how many grams of NH3 were produced. That comes out to 60.6 grams of NH3. Now that's if N2 is the limiting reactant. Now let's assume that hydrogen is the limiting reactant. So 50 grams of H2, hydrogen. The molar mass of hydrogen is 2.016 grams per mole. So that's moles of hydrogen. We know from the balanced chemical equation that 3 moles of hydrogen produce 2 moles of NH3. So that step got me moles of NH3, and then I'm multiplying by 17.031 grams per mole. And that's going to give me grams of NH3, just like in the previous calculation. And based on the amount of hydrogen that I have, I could get 282 grams of ammonia. Clearly, nitrogen is the limiting reactant here because I can only produce 60.6 grams of ammonia based on the nitrogen that I have. So I'm not going to produce that much. I'm only going to produce 60.6 grams of ammonia. Okay, so what's the percent yield? The percent yield is the actual yield over the theoretical yield. It's the ratio of the actual to the theoretical. Theoretically, I should be able to produce 60.6 grams of ammonia. How much could I actually produce? The problem tells me it was 56.7 grams. So if I express this as a percentage, which you often do, by multiplying by 100, that's going to give me 93.3%. So that's my percent yield. And if I did a lot of trials of this, and this was really consistent, that means that I would know that I'd have to overshoot by like 6.7%, I guess, to end up with the amount of ammonia that I really wanted to have.